Good afternoon to all of you. Myself Dr. Sachin Kadam, and I am giving expert talk on 1 week faculty development programs on recent advances in civil engineering organized by VJTI Mumbai and Ajmer Engineering College. So, due to some technical problem, we are not able to have the live interaction on Google Meet. So, what we have decided to send the recording of this lecture to all participants, and if you are having some questions, if the participants having some questions or some doubt, they can feel free to write on my email or ask me questions on my mobile phone. So, my topic of presentation is the structural assessment of existing railway bridge under current and high speed train loading using SHM technique. The purpose behind selecting this topic, that this is the I have decided to have this lecture as more informative compared to its technical content. So, I am not going to dilute its technical content, but at the same time I will try to make it more informative that one can easily understand. So, what I am going to present here. So, let us start with the presentation. I will start with the introduction and relevance, then structural health monitoring and structural assessment. Then the third point is about methodology, the case study for validation of methodology, implementation of methodology to real life problem, summary and conclusion, and with some references. So, this is the content of my presentation. So, what I am going to present today is some of the research work carried out at the Department of Applied Mechanics at Walchand College of Engineering, Sangli, about the structural health monitoring of the existing bridges. So, our MTech students are doing this work, and this work has been sponsored by the TIFAC. So, which is the initiation of the Government of India to help students to come out with some research output. So, I am going to present here the one prototype model case study along with one real case study of the existing bridge, and how to implement the real structural health monitoring system to have the structural assessment of that bridge. So, this is the introduction and relevance. So, the first figure I would like to share with you is the major bridge failure in Taiwan. The reason behind this I have taken from the Journal of Performance of Construction Facility of the ASC. So, if you look at this figure, then you can easily point out that the failure here occurred due to the scouring of the foundations, the scouring of the bed. So, during the heavy, so we can compare this bridge system with the human being. So, in the initial stages, when the human is a young one, so the assessment of or the medical checkup you can say, so that is required in limited manner. So, same is applicable for the structural system. So, at the young age the structure does not require any kind of assessment, but as it passes certain lifespan, it requires the frequent monitoring of some of the structural quantities like a deflection, strains, vibration, acceleration. The loss of the life is less by doing this particular exercise. So, as the Indian context, if you see the relevance, the infrastructure budget in a recent year 2020 is about 1.7 lakh crores. So, these figures I have taken from the Union budget of Ministry of Finance, Government of India. There are total 1,47,523 number of railway bridges, out of which the 37,689 bridges have crossed the life of 100 years or more than that. Means if you try to consider this or if you try to quantify this, then around the 25% of the bridges have crossed their life more than 100 years. So, these bridges are generally constructed by using the steel as materials in olden days. So, we are going to now focus on the railway bridge, where generally the steel girders are used to connect one particular abutment to the other abutment. So, the another important point is the heritage point of view. The heritage point of view or the importance of these particular bridges as per the heritage is concerned is very high. So, if you are going to replace that particular bridge at this point of time, then you are going to lose the heritage value of that bridge, and which is not good as per the heritage of our country is concerned. So, we are spending in short we are spending lot of money on this infrastructure development, and it is now need of time to focus on the cross verification whether the infrastructure that has been built by our engineers are intact or not. So, that is the main concern, that the weakness in these bridges are in terms of fatigue or corrosion. So, corrosion is very active in the areas near the sea or where the atmosphere having some kind of humidity. Otherwise, the fatigue is a general problems in all kinds of the steel bridges. So, this to fight against this corrosion, we are supposed to do the salt spray test, which is available in the metallurgy, or otherwise we are supposed to do the So, on the y axis you can see the cyclic stress amplitude, which is expressed in terms of SA, and on x axis the number of cycles are expressed. So, if you try to make a difference between the low cycle fatigue and high cycle fatigue, then the low cycle fatigue is active here in this particular region, which is non-linear region, whereas the high cycle fatigue is the fatigue effect which has the linear variation that you can see by this particular figure. After passing the cycles of 10 raised to 6, so after a particular point when the fatigue effect will be the predominant, when it completes the cycles 10 to the power 6. So, at this particular point the fatigue effect will become a stagnant, and which is called as the fatigue limit. So, after this reaching the cycle of 10 to the power 6, okay, if certain material is going to sustain the more load on it, then that particular effect is called as that material has infinite life. So, very important point. So, 10 to the power 6 is the number of cycles required, okay, and if that material is going to sustain that test, then the fatigue effect in that material is 0, as good as 0. But if it is going to have certain kind of failure, then it has having a finite life. So, this is kind of a bifurcation between the finite life and infinite life. The fatigue crack growth. So, fatigue crack growth can be expressed on the logarithmic scale. So, on y axis you can see the dA by dN, which is also popularly known as the rate of crack growth per cycle, per cycle, whereas on x axis you can have the delta k, which is the stress intensity factor. So, every times we are going to consider the number of cycles as well as the stress intensity. So, these are the two variables in the any fatigue study you can have. So, here you can see some threshold limit. So, threshold limit is that particular amount of stress which can be sustained easily without having initiation of any kind of failure. After this limit, the initiation of failure will be there. So, there are three different stages. One is the crack initiation, then the crack propagation and the fracture. The third one is the fracture. So, here the stiffness of this line in initial phase is very high. So, the crack initiation will be the steeper things to get. After that, it is having some kind of linear variation in case of crack propagation range, and finally, in fracture region also the stiffness is very significant, you can see. In short, we can have the difference between three different stages. We can easily say that in the intermediate state of crack propagation, we are having the much wider range of the fatigue. Okay. So, initial range is less as well as the final range is less, but in between the crack propagation indirectly what? If the structure is subjected to repeated kind of load and if the cracks develop in a structural system, then that particular crack is going to propagate for a longer period of time and then only it is going to fail. So, we are now going to focus on the structural assessment. So, structural assessment is a procedure utilized to check the adequacy, structural integrity and soundness of structure and their components. An assessment is made to evaluate the structure's current and future use. So, the important point is we are going to do the assessment to find out or to figure out the current and the future use of the structure. That procedure, that systematic procedure is called as the structural assessment. So, what is the difference between the Indian scenario and foreign scenario? Why this structural health monitoring study we are going to do after taking the photographs? If the photographs are little severe, then we are going to do the non-destructive testing on that particular site. And after doing the non-destructive testing, we are coming with some conclusion that there is a need of some retrofitting or this particular bridge requires this kind of strengthening and all those things. So, this particular method is not that much systematic. What the systematic method the foreign peoples are following. So, what they are doing? So, initially they are having the photographs of the failure, local failure on the bridge system. Then by using these photographs, they are deploying the SHM devices, SHM system in those weak zones to determine the deflection, strain, stress and other structural parameters. After determining those deflection, strain and stresses, the bridge is modeled using the relevant software and the effective loading on the structure is applied, which consists of live load, dead load, wind load and some other special load like seismic load or snow load if applicable. After application of these loads and to find the and identifying the weakness in the structure, we can able to comment on the structural safety of that particular bridge, and depends upon that comment the structural parameters are then employed in a simulation and it is checked for the fatigue kind of loading. So, in short, fatigue kind of loading means suppose road bridge is there, it is subjected to repetitive kind of loading every day. So, that is kind of a fatigue effect on the road bridge. So, similar kind of fatigue effect we can understand on the will be significant in case of the railway bridges, okay? Because as per the definition of fatigue, if a repetitive load is applicable after certain times, then the fatigue effect will be significant in any case. Then what assessment methodology we are following? So, the methodology is simple as what the methodology generally followed by the foreign scenario. So, we will visit the site to physical assessment of bridge, then we will collect the preliminary data, includes the drawing of bridge, the type of support, type of bridge and the year of construction. If the drawings are not available, then we will take the actual measurement on site. Then we will try to find out the current properties of the material used by doing some in situ test on site, okay? So, like non-destructive testing for masonry kind of structure or even for the concrete structure. Then we will do the non-destructive test. Some material like steel needs to be extract from a proper position, and we will try to find out the properties of that material. Then we will do the finite element modeling of the bridge, including the current properties of materials and simulation. Then we will validate the FE model by using the structural health monitoring system and SHM system. The results matching the FE model gets validated. If results are not matching, then obviously there will be fault or there will be defect in modeling as well as by in assigning certain material properties. So, this kind of a flow chart we are supposed to follow. If results are not matching, okay, so we are supposed to repeat the step, and finally, we will end up with the analysis and a retrofit measure. So, this is now the prototype what our student have developed at the Department of Applied Mechanics at Walchand College, Sangli. So, this prototype is constructed at our laboratory by students, and these are the descriptions of this prototype. So, it consists of it look like a 3-span bridge. It consists of a deck which has the dimension of 12 mm, 12 mm is the width of deck and 2 mm is thickness. The 2000 mm is the width of one bay. So, like the 3 bays are there. So, the grade of steel is Fe250. Then it consists of the eye girder, steel eye girder, which is ISMB 200. So, we are having 1, 2, 3 and the 3 on other side. So, 6 ISMB beams which has the length of 2000 millimeter, which has the material grade of Fe250. We are having the pier cap. So, the pier cap is nothing but this transverse beam. So, the transverse beam which has the section of 100 and 150 in cross section, and which has the length of 1200 millimeter, which consists of the concrete of grade M20. We are having the circular pier of length 850 and having the diameter of 150, which consists of M20 grade of concrete. We are having the rectangular pier base of 300 by 300 as a base, which has the 200 mm length, which consists of M20 grade. So, here you can see that this prototype has been constructed, and we are actually moving a trolley vehicle on this prototype from one end to other end by having this particular winch kind of arrangement or pulley kind of arrangement, you can say. So, we are going to consider the loading consideration or loading protocol by scaling up this particular model as per the provision given in the IRC 24 2010. So, IRC 24, that is Indian Road Congress 24, is a document which talks about the standard specification and code. Okay. At the same time, we are also going to consider the IRC 22, and we are going to come out as the bogie type of load, which is obviously the point load applied by the wheel on that particular platform, which is given in this particular figure. So, this is the maximum bogie load for the class 70R loads as per the IRC standard. So, this loading protocol we have considered in analysis of that bridge. So, this is the finite element modeling. So, we can see clearly what I have talked about little earlier. So, it consists of a deck, then we can see the 3 ISMB beams here. Okay. So, sorry, the 3 IS means 9 beams are there, okay, not 6, 9 beams are there. These are the piers, then these are the transverse girders. Okay. So, this model is generally this is the rendered view of model. The model has been prepared in a software Midas Civil. So, Midas Civil is the software used to simulate this effect of the vehicle. So, this is the moving load. So, this is the loaded trolley. So, we can load this trolley up to the 500 kilogram. So, 500 kilogram is the maximum limit, and we can move this trolley from one particular point to other particular point on this tracked platform. The platform is a tracked one. The tracked one means it cannot have the freedom to movement within this confined boundaries. So, the boundaries are confined by using this angle. So, this is called the tracked vehicle. So, we can able to now understand the simulation of the trolley load in Midas. So, suppose if I am going to consider the load on the load of the trolley as 100 kilogram, then this 100 kilograms is going to impart the in terms of the reactions in terms of point load, and there will be 4 point loads. So, here if you see this particular 100 kilogram trolley at this location, then it consists of 0.25 kilonewton, 0.25 kilonewton as the reactions at the wheels. And if you are going to if you are going to add the effect of all this together, then it will become the 100 kilogram load. This is the data acquisition system we have deployed to take a deflection reading. So, this data acquisition system we have used is taken from the NI National Instrument. So, the accuracy is very good. At the same time, this data acquisition system we can directly connect to the computer to take different points to restrict the movement of that vehicle apart from that particular track. So, this is called as the tracked vehicle arrangement. Then this is how we are we can deploy the deflectometer on the bridge model. While looking at this deflectometer, this is having a very good accuracy. So, this arm we have used to measure the deflection of central girder. So, central girder is going to deflect by some amount and that we can measure. So, this particular arm having hinge kind of arrangement at this particular end. Okay. So, whatever the correct deflection we are going to get, we can have. We have varied the loads in that tracked vehicle. So, we have started with the 100 kilograms up to the 500 kilograms and we have taken the 4 arbitrary reading at that particular central girder. So, these readings now we have measured in terms of microns. Okay. So, we have measured these readings in terms of micron. So, for 100 kilogram load, the deflection will be 98 micron, 92 micron, 103 and 103 micron. Okay. So, we can pass the vehicle and we can see the deflection in micron. Similarly, for 200 kilograms, for 200 kilogram these are the readings, for 300 kilograms these are the readings. So, these readings are being taken in micron and this is how we are going to get the output. So, if you see the accuracy, so this is having the maximum deflection at the center, at the same time as this is having the boundary condition which is generally simply supported, we can have the similar kind of effect in each bay. So, in each bay the central girder is going to deform more compared to the rest part. So, that is the actual observation during the experimentation. Therefore, we can say that our results are not going to exactly match with each other, but that is the count of millimeter. So, analytically we are getting this particular reading as a millimeter and this is experimental result. So, 0.242 millimeter and experimentally we are going to get this 394. One more point that you can understand, that the experimental results are always little conservative, that what we have observed in our this trend also, which is quite correct. The important task now I would like to discuss with you is the development of these two units at our institute. So, as I told you, this project is a collaborative project between our structural engineering group as well as the students from the mechanical engineering and some students from the computer science. So, this is the ultrasonic sensor what the students have developed. Now, the idea behind this ultrasonic sensor is the continuous reading, continuous readings on the real bridge is very difficult task and it will result in a huge data. So, what the idea we have used in this particular experimentation, that or we are going to use in a real life, that whenever the railway will reach at a particular point, this sensor will trigger automatically and after triggering it, the accelerometer will come in picture and that will measure the acceleration. So, the data available with the source will be minimum. So, whenever the railway will pass on the bridge, then and then only it is going to measure the acceleration. By other times the acceleration will not be measured. For that purpose we have developed this ultrasonic sensor. So, how this ultrasonic sensor is going to work? So, this is having the two transducers, one is the transmitting transducers and one is the receiving transducers. So, one transducer is the receiving end and other is transmitting end. So, we are going to transmit certain rays, okay, certain rays. So, those rays are obviously the ultrasonic rays and those ultrasonic rays will transfer which travel with some velocity and we can able to compute the velocity of that particular rays depends upon the distance and time. So, here it is given that this waves will strike on object and this will again come back to the original position, and based on this particular logic we can able to develop the velocity parameter. So, here this the circuit is again prepared at our institute. So, which consists of the Raspberry Pi 3B circuit. So, here also you can able to see the two transducers, one is a receiving and other one is a transmitting transducer. So, this circuit, what is the use of this circuit? So, this particular circuit is being deployed at actual site, need not have a computer requirement at site. So, by using this Raspberry Pi circuit we can able to take the output. So, in short I will try to explain you what our student had programmed by using the Python program. So, they have used the Python or Arduino code to do the programming. So, I will explain you what is this program. So, as I said you, there are 2 points, one is there are 2 pins, one is echo pin and one is a triggering pin. Okay. So, the triggering of the accelerometer will start at a particular point, okay, when the echo reaches to the required extent. Then it will again going to have the output and input parameter. Okay. Here you can see this is a program that is, this is code written in Arduino Python base. Here you can see that this is important fact that one can understand. So, this is the distance which is equal to duration into this. So, what is this? So, this is the velocity of that particular ultrasonic rays. So, velocity of ultrasonic rays is generally we can see in literature, on you can also Google the things. So, it is 340 meter per second, 340 meter per second. So, how it becomes now 0.035. So, if you see, so what the program they have developed. So, if you are going to use this Raspberry Pi as a circuit board and these 2 transducers, then finally we are going to end with the maximum deflection, that is all. So, we are not going to play with the velocity and acceleration and all those. So, final output what we are going to get will be terms of centimeter. So, what will be the displacement? So, here I will explain here. So, 0.034 is a particular velocity. So, final output we are getting in centimeter. Therefore, the 340 meter per second has been converted into the centimeter per microsecond, and this is divided by 2. So, by considering the average, here it is given the speed of sound waves divided by 2. Okay. So, it will have, and this repetition will took place on a platform, okay, for the 10 microsecond. Repetitive load is applicable or applied on a platform for each 10 microsecond. So, this is kind of the mounting ultrasonic sensors we have established at our institute. So, we can see here this is isometric view, this is the front view and this is the side view of this ultrasonic sensor, and this is the accelerometer actually we have deployed at our prototype model. So, this accelerometer we have deployed to measure the acceleration here at our prototype model. Now, other important aspect of this structural health monitoring, I will try to explain you in very simple structural mechanics, in language of very simple aspect in structural mechanics. So, what is the important fact in the fatigue analysis? The fatigue analysis, if you see the graph of the fatigue, then we are having the requirement of 2 important parts. What are those 2 important quantities or 2 important parameters? One is the stress or strain, the other one is the number of cycles. So, if we are going to get the stress as well as number of cycles, we can able to plot the SN curve. So, here by using the simple bending theory, we can going to have the establishment of this stress parameter. How? Let us see here. So, we are having this equation which is the simple bending theory. The stress, sigma is the stress, E is the modulus of elasticity, y is the distance from the neutral axis and r is the radius of curvature. Okay. So, m upon I is equal to sigma by y is equal to I by r. Now, the interesting part is, if this structural system is subjected to central point load, it is going to give the maximum displacement at the center, and the maximum displacement or maximum deflection at the center is obviously WL cube by 48 Ti. is it not? So, at the same time we are having the maximum slope at this two end and the value of the slope is WL square by 16 EI. Now, we have I have drawn here the deflected shape of this beam by considering the point load here, and the maximum angle will be subtended at this particular point, which is the theta A and theta B. The theta is the slope. Here the theta A and theta B are should be equal, okay, as this is having the symmetrical kind of things away from this point load on this particular half section and on this right hand section. Therefore, the theta A and theta B will be the 3 delta C divided by L. So, why this 3 delta 3 by L delta C? So, delta C, if you are going to substitute the value of the delta C here. So, what is the value of the delta C here? So, it will be the WL cube by 48 EI, and if you are going to compensate that L and 3, obviously we are going to get the value of the slope, which is WL square by 16 EI. What is use of this? The further this equation we are going to utilize for more understanding in terms of the stress or strain. How? Let us see here, the L is the length of this particular arc, okay, because of the application of load. So, this L will become 2 r theta, the theta is the slope, okay. So, not exactly 2 r theta, but it will become 2 r sin theta. This theta is very small, we can ignore that and we will assume that the L is equal to 2 r theta. What is the theta here? The theta, as I explained you, theta is equal to theta A plus theta B. Hence, the r will become L divided by 2 theta, r will become L divided by 2 theta, and if you substitute that particular r in earlier formula. So, we are going to get the sigma, which is our earlier formula, sigma that E y divided by r, which is equal to sigma. Here E and y are known, so sigma can be found out by knowing r. So, verification. So, the same thing we have verified in the software, I will explain in few minutes. So, we have considered the beam which is simply supported of size 100 by 50, the length of beam is 2000 millimeter, the central point load consists of 100 kilonewton, it has the modulus of elasticity 2 to the 10 to the power 5, means it is made up of a steel. By using these formulas, we can able to compute the maximum deflection or the maximum deflection value of stress. The value of this sigma, the value of stress is 1.33 megapascal and the deflection value is 0.029 millimeter. Not we are to validate this, we have made the model in Midas. So, let us see this model, the same thing what I have said you, the 100 by 50 cross section of 2 meter length subjected to central point load, and this is the deflection of the beam. So, if you see the deflection of the beam 0.029 at this particular point, and if you see our quantity by our equation. So, we are also having the same formula or the same value. So, here this value, not only the deflection, but in terms of stress also, this is the stress limit. So, what is the stress value? Maximum 1.33 megapascal, is it not? We can see this particular as a maximum value shown by the red color, and if you look at this contour of the color code, then the maximum value we are going to get is 1.33. The similar value we got from this formula 1.33 megapascal. Indirectly, by using only the deflection parameter, we can able to find out the stress in a particular. This is the permission letter we got from the PWD department, or not PWD, from the railway department. So, railway department has given us a permission to do the health monitoring of a particular bridge. So, this is the photograph of bridge. So, this is the railway bridge under study. So, we can see here. So, this is the bridge from Miras to Kolhapur section of the railway. So, we can see here the railway is running there. So, we have taken the photograph here. So, one road bridge was there, and adjacent to that one railway abutment. This is abutment. So, here you can see the pier. So, this data we got from the Indian Railway. So, this is the soil test report we got from the Indian Railway. So, you can clearly see that they have carried out the exploration, soil exploration about 20 meter in soil. Okay. So, this is this particular level is 1766.62 and this is 1746, means about 20 meter depth they have explored here. So, this is towards the towards the Kolhapur end abutment and this is towards the Miraj end. So, the bridge is located between the railway section from Miraj to Kolhapur. Now, this particular segment of railway is operated on the broad gauge. Okay. In terms of broad gauge, the broad gauge line is there, and now the railway is trying to have the certain kind of fast vehicles on that particular track. So, this is the old bridge for the meter gauge, the modification of meter gauge to broad gauge. So, during this particular modification of meter gauge to broad gauge, some strengthening is carried out obviously to these piers and these piers you can see here. Now, for developing of this particular model, we have taken the actual measurement on site. So, our students visited the sites and they have taken the actual measurement of each and every part in detail. Let us see here, the students visited at these locations and they have tried to find out the actual measurement of each parameters, because we are that they are going to model this bridge in the MIDAS software. So, all the details they required. They have used the advanced measurement unit like laser tape. Okay. So, laser tape is generally used for measuring the distances. Even we have modeled the accuracy in terms of railway sleepers also. By considering the dead load of railway sleepers, we have tried to see the distances between the railway sleepers or the concrete sleepers we can say, okay, by using this laser tape. So, laser tape is this particular instrument, we can easily measure the distances by focusing or by targeting a particular object with the this particular laser tape, and it will automatically give us a distance, accurate distance. So, this is the 3D model of this small part of bridge. This is a computer model of existing railway bridge. This is the model. So, if you see this girder, it consists of the plate element as the major part. This is the 3D model of the girder. This 3D model of this is the view of this girder. We have also carried out some of the important material tests as per the permission of the railway. So, we have carried out the tension test as well as the chemical analysis of the material. So, we have extracted some of the specimen from the bridge girder, actual bridge girder. So, let us see this to understand the existing condition of this structural material, that is the steel. We can see the corrosion of specimen and we can also observe the reduction of the cross section. So, already the bridge have crossed the more than 90 years as per the records, or near about 100 years. So, these are the tests we have carried out in our laboratory at Walchand College. So, the arrangement for the tensile test at the UTM, and this is the load versus displacement curve. So, nice curve we are getting here. So, we can point out the important values here. So, we are going to get the yield stress as 250. So, the steel conforms to the grade 250, what the railway said. Railway says that it is consist of 250 megapascal, which is correct. The yield stress is 250 megapascal. The tensile strength is 427. The elongation at the break is 48. The reduction is 20.80%. The reduction is 20.80%. You can understand. Okay, and the elongation is 22%. So, this is the load versus deformation curve. So, by in simulation also we can give the input as modulus of elasticity, which is the slope of this graph, okay, and as well as the yield stress of the material. So, this chemical analysis is also carried out in our metallurgy laboratory by using IS 2062. Here this is I section of the girder, what we have taken from the actual bridge. There is a as per the ASTM standard, American Society of Testing Material, this particular girder we are supposed to make in a particular samples by considering the 1/3 from this particular end as well as 2/3 from the center of wave. So, that particular part we have extracted in the laboratory. We have these are the test results. So, by looking at the actual chemical analysis, we can able to classify the different element like carbon content, magnesium content, the sulfur, phosphorus and silicon. So, all these values are within range except 2, sulfur and phosphor are not in within. So, we have discussed with the experts, and they come up with the options that if the values are not within the limits, this particular material is not suitable for welding. So, that is their conclusion. Means for strengthening now, we are supposed to search out some other kind of option, okay. Or if you are doing some kind of welding, some other extra special kind of welding we are supposed to import if the bridge is not safe. So, this is Millar's model. This is load case. So, dead load, then the superimposed dead load, seismic load, wind load, braking load, response spectra, and all those moving loads. So, I will just explain the seismic load. So, every standard is being discussed here. So, IRS means Indian standards of Indian railway standards. IRS means Indian railway standard. So, this is for seismic code. So, zone factor is 0.16, zone 3 as per the location is concerned. The influence factor is 1.5. In the standard says that the table number 2 is there. Always you are supposed to take 1 point. Important value is this R is 2. Now, we people are knowing that the value, the formula is Z by 2 into I by R into SA by 2, and R we are going to consider in denominator, which is significantly low. Okay. For our SMR building, we are going to consider the R value as 5. Here we are going to take the value as 2, means the force will be enhanced one, the force will be significant, because the value at the denominator is less, that is the case. We are getting the SA by G as 2.5, and this value of the damping is 1.4. Why 1.4? Because this material is steel material. The damping for 5% for concrete is taken as 1, for steel it is 1.4, and for masonry it is 0.8. So, 1.4 is value. So, the wind load, the railways code is silent about the wind analysis. So, we have considered the IRC, Indian Road Congress, and accordingly we have carried out these particular values. Okay. So, I will move further, I will not discuss this. This is wind load, we are applied here at this particular location. This is braking load and moving load. So, braking load is actually the movement of railway vehicle on the actual railway track. Okay. So, this moving load is considered as per the bridge rule 2014. So, there is one document, bridge rule, published by Indian Railways, where you can find this document how to consider the moving train load on the structure. So, this is the braking force. So, the results are now we can understand the result. So, this is the maximum displacement. The maximum displacement or deflection we are going to get is 9.5 millimeter. So, here you can see the unit is millimeter. The maximum deflection is 9.5 millimeter at this particular location, and if you compare this, so as per the IRC 624/2001 clause number is also given here 507.5.2.5.2, the permissible deflection is given by the code as L by 800. So, which is 19.5. So, 19.5, the 20 meter is that particular length of short bridge. So, 20 meter 19.5 is the two ends where it is having the supports, divided by 800 comes to be 24.37. We are getting the 9 mm, which therefore, our bridge is safe. We can comment that for present condition our bridge is safe. This is the 11 forces, we can able to quantify these particular forces any time. So, do not go towards this colors. So, the color in red is not the element which is going to fail. Okay. So, this is the maximum tensile force, and this maximum tensile force is now 4.52 10 to the power 4 divided by the cross section area. So, generally that I have checked this particular color. Therefore, the here the angle section is 150 by 150 by 12 mm. So, angle, what the angle they have used actually, the value of that area of that angle is as per our code, is 0.586 millimeter square. So, you can able to quantify the stress, and the stress should not be more than 250 megapascal. If it is going to exceed 250 megapascal, it is going to fail, because that is the value of the yield stress. This is the place stresses. So, these are the mode shapes. Now, we can able to see the mode shapes, how the bridge is going to behave. So, let us see in 1 minute how the bridge is going to behave. So, this is about the mode 1, the translatory mode, you can see the time period and everything there. So, the first mode is the translatory mode, then we can see the second mode. So, second mode also should be translatory in other direction. So, it is also kind of transverse movement, and the third mode should be the torsion or rotational mode. So, we can see this mode also. So, this is having some kind of torsion. So, these are the mode shapes. Then I will talk about the high speed train in 10 minutes and we will stop. This is the International Union of Railway, the high speed because the question was whether this bridge is good enough to use for the high speed train, okay, or if the velocity of the train is exceeded certain limit, whether we can use the existing bridge or not. So, that was the concern of Indian Railway. So, this is the picture of the high speed train generally. So, this red dash shows the high speed train in operation. So, if you see these are the view at glance worldwide. So, you can see that this network is very dense in this particular part, which is the European part of world. In Europe you can find the high speed train, okay. So, in this particular place is China, okay, and this is the Japan, okay. So, high speed train is operational in this particular part of world, and now this is India. So, we are also thinking of the high speed train project. So, therefore, we are having this particular current. So, this is the future expansion of the high speed train. So, the very good benefit of high speed train we are going to get, we can compare the benefit of this high speed train or in terms of economy, energy efficiency and CO2 emission. As per the economy is considered, it is economical one, the solution is economical per 1000 passenger per kilometer. We are going to get the economical as compared to the bus, then followed by the flight or air mode, then by individual car. So, these are some of the points to be considered to compute the economy of this operation. So, climate changes, urban effect, nature and landscape, air pollution, noise and accident. So, these are some parameters included here. As per the energy efficient is concerned, the train is most efficient, okay. It is given here, passenger kilometer carried per unit of energy. So, for 1 kilowatt of energy we can transfer, we can travel 170 people, 170 passengers by train, and for flight it is only 20 people. So, the energy efficiency is considered, the train is economical one, followed by this all transport modes, okay. And this document is I have considered from the European Union of Railways, they have published this document. Then the CO2 emissions, carbon emission is main concern now worldwide. So, our this high speed train for 100 passengers, the emission of carbon is 4, okay. So, the 4 kilogram of the carbon is emitted, okay, for 100 passengers if you are using train, and for flight it is for aeroplane mode it is highest of 17. Then this is a development of high speed train. So, in high speed trains we are now marked this landmark of 574.8. In 2007 the France has tested this high speed train and the maximum recorded speed was 574. Initially in 1830 the speed was less, 48 kilometer per hour. So, as per the Indian contest is concerned, we are having the fastest train which operates from Delhi to Jhansi, okay. So, that Gatiman Express is name of that train, okay, Gatiman Express, which has the velocity of 160 kilometer per hour, 160 kilometer per hour, that is the highest train in operation in India, followed by Vande Mataram. So, this is having the similar kind of range, okay. So, 160 kilometer per hour, but this particular France, so they have already tested for 574 kilometer per hour. So, high speed train loading reference Eurocode 1 is giving the significant amount of information about this high speed loading. So, this is very interactive now. So, this is the traffic load on the bridges. Okay. So, here we can give we can consider this particular loading protocol. This is called as the loading protocol. So, I will explain in 1 minute what is this. So, this is the standard and light traffic mix. So, type 1 is locomotive hauled passenger train. So, this is the summation of Q, means this is the total weight of train 6630 kilonewton. This is the maximum velocity it can attain. So, it can attain velocity of 200 kilometer per hour. This is the length of train. If you summarize, if you add all these things, then it will come as a 260.10. And what is this small q? So, small q is the UDL. So, this divided by this, that will become the UDL over the entire track. So, this is a loading protocol for type 1, this is loading protocol for type 2. So, obviously, there will be change in the total weight of train as well as the length, therefore, the q will be different. Okay. So, this is the type 3 train, type 4 train. So, we will consider the type 3, the high speed passenger train in our analysis. Okay. So, as per the inquiry from railway, so 250 kilometer per hour. So, there what the speed they are expecting that the system or the bridge can sustain. So, the important task is now to consider this loading protocol on actual bridge. So, this is given in the MIDAS has a provision to do the transformation of the moving load to the dynamic load. So, we are supposed to convert this loading protocol in a time history manner, then and then only we can give as input to the software as a time history. So, MIDAS has that provision, therefore, this is the input for the type 3 case we have considered, and this the MIDAS will end up with this particular time history, and we can directly now supplement this time history to the software to do the analysis. So, this is how that this is the last slide what I want to discuss with you. Then this is a concluding remark. What I want to conclude, what I want to conclude now is the SHM technology we can validate for the FE model for the bridge by comparing the deflection results, and once the FE model is get validated, it can be analyzed under current and high speed train loading, which will predict the structural safety and also address the need of retrofit if required. These are some references. So, time is approaching towards 1 hour. So, I have to stop here. So, let me excuse for certain reasons that somewhere I have purposely accelerated, and the clear results of that bridge under considerations I have not shared with you, since I supposed to follow some publication protocol. But if you are having some doubt about this presentations, you can write me on my email, or you can contact me on my phone also, and I will be happy to share the required information to you. So, thank you for the patience, Dr. Vikas Varekar, to ask me to prepare for this presentation, and I will